Hey there, Chem Squad. In today's class, we're going to look at rate determining step. In the previous class, we looked at reaction mechanisms, which is basically a series of steps that makes up the overall reaction. Now, if we want to figure out what the overall rate is of that net reaction, we have to look at something called the rate determining step. Now, out of all the steps in your reaction mechanism, the slowest step is often identified as the rate determining step. The rate determining step is basically a step that involves making an intermediate molecule. So remember, it's one of those in-between molecule or transition molecules, but it's the one that requires the most amount of energy to make. So if you have to add a lot of energy to make this intermediate molecule, it will naturally have the most amount of stored energy, and therefore because it requires so much energy, it requires a lot of time to make it. So let's look at an example of a reaction mechanism. So here it's a three-step mechanism. I don't have the net reaction just yet, but since we're talking about how much energy it takes to make an intermediate molecule, let's say, for example, that in order to make N2O2, that's an intermediate. Let's say it requires something along the lines of 100 kilojoules of energy. Now, in order for the second reaction to proceed, it's going to make a second intermediate between step 2 and 3. Let's say this second intermediate requires 200 kilojoules of energy in order to create. And then finally, in the last step, since there's no intermediate being made, the molecules still have to react with each other, so some energy will probably be used up. Let's say it only requires something like 20 kilojoules of energy to complete step 3. So it takes 100 kilojoules to complete step 1, 200 kilojoules to complete step 2, 20 kilojoules to complete step 3. So out of all three steps, this one has the most energy. And because it has the most energy, it will require the most time. So if it requires the most time to create this intermediate particle or molecule of N2O2, then this is the rate determining step. So if we were to look at the overall net reaction, if we kind of translated the amount of energy to the amount of time, let's say it took about 100 kilojoules, so let's say that equates to 30 seconds. 200 kilojoules could be 60 seconds. So then if you have 20 kilojoules, that could be, let's say, 5 seconds. So when we look at the net reaction, we cancel out the intermediates. We double check to see if there's anything else that we can cancel out, and there isn't. So we just collect the molecules that we have on both sides of the reaction. So in this case, the net reaction of N2O2 plus 2H2 will give us 2H2O plus N2. So that's a net reaction, and the total amount of time that it takes, you just add up all the time, and it would be 95 seconds, which would be the overall time. So if it takes 60 seconds for the slowest step, so step 2 is the slowest, this one single step determines the overall amount of time that it takes for this reaction to take place. Thus, if I wanted to increase the rate of the reaction, I can add a catalyst, okay, but that catalyst has to affect the slowest step. So adding a catalyst to step 2 to the slowest step will increase the overall rate. Okay, so if we can get that 60 seconds down to even 40 seconds, that'll be a much faster reaction. However, if I add a catalyst to a step that's already fast, it may decrease the amount of time from maybe 5 seconds down to 4 seconds, but it wouldn't do much to the overall rate. Okay, so if we ever want to add a catalyst, we typically want to find a catalyst that will quickly speed up the rate of the slowest step. So let's take a look at an analogy. Okay, there's actually 2 analogies that I want to look at. The first one is hill walking. So in this analogy, we're going to try and do the same thing. Okay, try and show what is the slowest step in this multi-step process. So in this analogy, there are 3 hills. Okay, you are standing right here at the plateau at the very beginning, and you want to climb up this first hill. Well, the first hill has a certain height to it. Okay, it might not be that high compared to the second hill. Okay, so it might not take you that much time to go up it. So let's say it takes you about 1 minute. Okay, by the time you get down to the bottom, you have another hill, and this hill is significantly taller than the first one. So logically, it would take you more time to get up the second hill. So let's say it takes you about 5 minutes to go up the second hill. And usually going down is fairly quick, because going downhill is always fast. So when it comes time for you to move up the third hill, the third hill is the smallest hill. Okay, so maybe it only takes you 30 seconds, okay, to go up that small hill, okay, and then come all the way back down. So it takes you 30 seconds to go up the hill and down the hill, 5 minutes to go up the hill and down the hill, and 1 minute to go up the hill and down the hill for that first part there. Okay, the total time is approximately 6 minutes and 30 seconds. Okay, but what is the rate determining step? Well, it has to be the one that took the longest, the slowest step. So the slowest step here equals the rate determining step for the overall rate of the reaction. Okay. Now, I like the hill idea, okay, because it mimics what happens to molecules when they have to have a certain amount of energy in order to form intermediates. And if we haven't gone to that already, we'll get to that in a future lesson. But I want to offer you a second analogy. Okay, for this second analogy, instead of walking up a hill, let's say you are involved in a 4x100 relay. So you have to run 100 meters, okay, and you're part of a team. Each person has to run the same distance. So let's say that Kate, the first runner, takes only 15 seconds in order to finish 100 meters. Okay, that's pretty fast. But Lewis is even faster. He takes about 12 seconds. Now, Joseph, the third runner, he takes about 20.5 seconds. Okay, maybe he's just a little tired that day, but for whatever reason, that's a significant amount of time to take a 100-meter race. Now, Sarah is the last person to run, okay? And her time is only about 13.5 seconds, okay? So even though Sarah's not the fastest runner, okay, she's not the slowest either. So she's not going to really affect the overall rate. That glory belongs to Joseph. So since he is the slowest at this particular race, he would be considered the rate determining step. So the net time, okay, you would simply have to add all the times together, and I think it just comes out to be 61.0 seconds. So they could have run a little bit faster, but because of the rate determining step, the slowest person, it takes them much longer. Okay. Now, you could potentially figure out an analogy for a catalyst as well. So a catalyst tends to speed up the rate of reaction. Okay. But again, the catalyst has to be applied to the slowest step. So in this case here, if I want to add a catalyst to help Joseph run better, he might be given some steroids, okay, illegal substances, something that will speed him up. And if it works, if he can get his time down from 20 down to like, who knows, like maybe like 12 seconds, that would affect the overall rate significantly. Okay, so these two analogies, okay, are decent analogies that we can use to explain rates of reactions. Now, I want you to create your own analogy for rate determining step. I don't want you to use the two analogies that I've given you today. Okay, so you make up your own, but just keep in mind, for your analogy, it has to have multiple steps. Okay, and it has to be clearly shown which step is the slowest. So you have to identify the slowest step. Okay, so you can look at things like from your daily, everyday actions. Okay, getting ready for school in the morning. Okay, a lot of people have used analogies in terms of baking or cooking. Okay, even doing your hair. So there's a lot of choices out there. I just want you to create your own analogy, okay, for future use. All right, that's all the time I have for today. See you guys soon.